Okay, so I'm just going to talk to you a bit more about temperature, this time rather than biology, about the technology side of it. So it's Temperature Technology 101. How is it managed and why does it matter to the crop? So the top 5 most important things in post-harvest horticulture are temperature, relative humidity and gas atmosphere. So that's a very common saying, and it's actually universal. It's the truth. If you get temperature right, the other things tend to look after themselves to some extent. So what is temperature and how does it move about? So we've talked about heat in the previous biology talk. This is just an example. We've got an example there of a fruit where we've got a fruit exposed to direct solar radiation, diffuse solar radiation. So that is point 3 on the method of movement, so heat transfer through electromagnetic waves. Then we've got conduction. Point number 1 up there is heat transfer through the objects itself. It can be a cool room wall. It can be a product adjacent to another product, so it moves through through product packaged in a container. And then there's convention, where hot air rises when people like me talk, and it goes around, cools down and comes back down. So they're the main mechanisms of heat movement. So in terms of temperature management in the post-harvest chain, what do we need to consider? We need to consider 2 things. One is cooling the product, getting that heat out of it, and the second one is storing the product, maintaining it at low temperature. So methods of cooling can be fast or they can be slow. So if we just put a carton into a room and leave it there to cool, it takes a long time because you're relying on conduction of heat to come all the way through. If we have a pressure cooling or forced air cooling, if we run the cold air through the container, we cool the product very quickly, and Lynn touched on that before. So fast cooling is the ideal way to go. Methods of storage, the cheapest is refrigerated storage. We can go up in cost with controlled atmosphere storage. We can go up or sideways in cost with modified atmosphere storage, and Roberto's touched on that in terms of modified atmosphere packaging. The infrastructure is really important. If you want to put up a low-cost cold room, you can get 75mm laminated polystyrene and build it on a concrete slab, put a refrigerator unit on it, and away you go. But you're going to be paying an awful lot in electricity bills to do that. On the other hand, if you get 150mm thick laminated polystyrene, you put a false roof over it, and you run the system protected from direct solar radiation, your energy bills will drop like crazy. So how you build your infrastructure is important. The design of the structures, also the capacity. When you build a post-harvest facility, a rule of thumb is build it twice as big as you're going to need, because you're going to expand. Don't plan to contract, plan to expand. And the cost of expansion is less if you're building a unit that's got the capacity. It's always best to build a cubic structure because the cube gives you the most volume for the surface area of the structure. So the design, structures, capacity, and then the operations. Make sure that you've got people that can operate it and know what they're doing. It's a specialist area. I know a company that brought in their field operations manager to run their post-harvest facility. In the first week, they lost $50,000 worth of rate, so because the person didn't know what they're doing. So that's important. And then logistics. So it's all about product flow. So again, when you're designing facilities, you need to make sure that you've got product out of the field. It goes under shelter, so that it's not sitting in direct sunlight. That it can flow into the post-harvest facility and move straight through that facility in a relatively linear fashion. That gives you the most efficient logistics. I think Lynn put up this picture before, which is about the forced air the cooling curve. So the big thing there is the 7/8 cooling. When you're going to be cooling product, you cool it down to 7/8 of the temperature differential from when you brought it in and what you're trying to achieve. The last 1/8 of cooling costs you more money in energy than it's worth it. So 7/8 cooling is really important, irregardless of what method you're using for fast cooling the product. These are the range of methods that can be used for cooling products. So room cooling, not very efficient, might be all right for pumpkins or something like that, which has got a really long inherent shelf life, but not for short-lived products like, say, asparagus. Forced air cooling is really good. Hydrocooling is also really good. Ice cooling is arguable. It depends on how you do it. I'll just talk a bit more about these things in a minute. Vacuum cooling is really good. Cryogenic cooling is where you're using dry ice or liquid nitrogen as your refrigerants. And then evaporative cooling is where you, like in Western Australia where humidities are low, you can put an evaporative cooler on your house and you get the same sort of cooling effects as if you've got a reverse cycle air conditioner in a place like Queensland where the relative humidity is high. It can be used for cooling citrus, for example, grown in semi-arid areas. Okay, but the main methods are room cooling, forced air cooling, hydrocooling, package icing, vacuum cooling, and transit cooling. First of all, I'll say in the bottom right-hand side there, transit cooling is a load of rubbish. Trucks are not made to cool product. Trucks are made to maintain the temperature of the product that goes into them. So anybody who thinks that they can fill a refrigerated truck with product and cool it down is fooling themselves and doing their customers a disservice. Room cooling only really applies to product that has a low rate of respiration and can take a significant period of time to cool down, a matter of days. So it doesn't work for products that have a high rate of respiration. Package icing, if you put an ice slurry through a package, which obviously it needs to be a package that can take the ice slurry, so it needs to be a fully waxed cardboard carton or a plastic carton of some sort or crate, that's fine. But if you just do top icing, they actually, again, fooling yourself because you get a crust of ice across the top of the product. That actually then forms an insulation layer between the product below, which is respiring and warming up, and the ice. So it just gives you a thicker barrier for temperature loss. So not a good idea. Forced air cooling, very good for bulky products, so it works fine for things like tomatoes. Hydrocooling, really good for product that can, it's the fastest rate of cooling because you've got cold water in direct contact with all the product, but it's only good for product that can tolerate being wet. And then vacuum cooling is really good as well for high surface area product like lettuce, because you've got a high evaporative surface, so when you evaporate water, it causes cooling, just like when you sweat and you've got wind blowing over your arms, you feel the cooling effect. So this is just some comparisons of some methods here. So we're looking at the typical cooling times. So the extreme over here is 20 to 100 hours to cool by room cooling, compared to 1 to 10 hours by cooling by forced air. The more fast systems, about 0.1 to about 2 hours cooling for hydrocooling, vacuum cooling, and water spray. And I mentioned before that the icing is okay if you do it with ice slurry, but if you've got top icing, it can take a lot longer. So it's a no-no. So different crops have different preferences for cooling, if you like. So, so over here on the vegetables, we've got, for example, Chinese vegetables do very well with forced air cooling. Things like cucumbers are really good for hydrocooling because they're relatively water resistant. Where am I now? Brussels sprouts, good for vacuum cooling because they've got a high surface area of leaves, or little leaves, but leaves nonetheless. And then room cooling, things like tomatoes I've just mentioned. So the breakdown by method is important. So just a summary of the cooling considerations. We need to think about the product type. We need to think about the effectiveness of the method of the system. So the method of cooling, design, build and operation specifications of the facility, and the cost in terms of money, particularly for refrigeration, and also for carbon costs as well. So the amount of energy that's being consumed. For efficiency, the key is to look at the 7/8 cooling time and make sure you don't try to cool beyond that because you're throwing money away. And then the facility is the design, build, operation specifications. But the other thing that's really important here is the cross-docking. So making sure that when products moving through the chain, you can cross-dock in a similar refrigerated environment. So you know with the DCs, for example, you can back the trucks up and the sort of pillow packs come out and surround the truck, and you can pack from a refrigerated environment into a refrigerated environment without getting product warming. But product warming during cross-docking is a big problem. You see, for example, products sitting, going export by air and sitting on the tarmac. Products supposed to be tracked at, say, 0 degrees C, so something like broccoli, which is shipping overseas, tarmac temperature might be 55 degrees centigrade, so you get a fair bit of warming in a fairly short period of time. For the vegetable crops we're talking about, particularly the leafy vegetable crops, there is a bit of an exception. So I talked before about temperature. I've kind of de-emphasised it here and emphasised relative humidity because water loss is a big issue from fresh produce like lettuce. So there's a wet coil refrigeration system where you actually put water with an antifreeze in it over the coils, then the air passes through a matrix that's wetted, and then it picks up moisture at the same time as it releases its temperature, its heat into the cooling medium, and so you get cooling but also maintaining a high relative humidity. With dry coil refrigerations, because they frost up and then you need to defrost them, you're actually pumping water out of the product onto the coil and then draining it out of the cold room. So not a good thing to do. And then that's and then nothing. It's question time. So if you've got any questions, please let me. Any questions? Otherwise, I've got one for you. No questions? All right. So the question is, what's the best method to cool mushrooms? I think. Sorry?
Fan forced cooling.
Fan forced is good, but not the best. Another guess? Okay, I'll put you out of your misery. It's vacuum cooled. So they've got a high surface area, a very high rate of respiration, a very high surface area. For a little bit of moisture, you get a lot of removal, and they can shrink a bit so you don't see it. You get very efficient cooling of the product. So that's it. Thank you very much. And I'll ask for the next. Thank you.